Good afternoon. I'm going to be speaking about some recent work that we've been doing in the WIZer project concerning data-driven approaches for parameterization of equivalent circuit models. This work is in collaboration with Williams Advanced Engineering, ZapGo, CodePlay, and Silver Power Systems, and is funded by Innovate UK. We're interested in constructing reduced order models for cells to be utilized in battery management systems. In particular, we would like our models to be accurate and robust. They should reproduce the experimental data used in training and generalize well to unseen testing data. The models should also be parsimonious. Unnecessary dependencies and degrees of freedom in a model hinder parameterization efforts. It is very important the system is simple enough to simulate in real time on a BMS and is amenable to state of charge, power, and health estimation tools. The quality of the state estimation is heavily reliant on the quality of the model and its parameterization. I'm going to be focusing on equivalent circuit models, an example of which is shown in the diagram here. Equivalent circuit models are not based on physical or mathematical derivations, but were originally constructed on an empirical basis to reproduce the frequency response characteristics of a cell. The circuit model can be expressed as a differential algebraic system, with the voltages across each RC pair being hidden states that are not obtained as outputs. These overpotentials encode different electrochemical processes, each with different resistive, capacitive behaviors. The resistors, capacitors, and OCV are dependent on the operating point of the system, including state of charge, temperature, and cell degradation. The task is to parameterize this model by constructing lookup tables which provide values for the circuit parameters as the operating point varies. These lookup tables are then linearly interpolated between the given breakpoints as the operating point varies. ECMs are low-dimensional linear systems, albeit with variable coefficients. Batteries, on the other hand, behave non-linearly and are most accurately described by high-dimensional physics-based models involving partial differential equations. For these reasons, it is unreasonable to expect ECMs to agree well with experimental data for all current inputs and operating points. To add to these issues related to model deficiency, the fitting of these types of linear systems is ill-posed, meaning that it can often be difficult to find a unique optimal solution for a given data set. I'm going to briefly discuss the current approaches for parameterizing these reduced order models and then elaborate on how we're approaching the problem anew. Typically, ECMs are parameterized using a combination of constant current and pulse current loads. The most widely used fitting methods are tailored for these experimental data inputs, which simplify the problem extensively, reducing the parameterization of a differential algebraic system to a curve fitting task at steps in the state of charge, with other components of the operating point, such as temperature and current magnitude, being fixed. Although this curve fitting approach is more simple and quite attractive, it remains an ill-posed problem. Drive cycles are then used for testing after the model has been parameterized. In practice, these approaches often show good results, but are susceptible to overfitting due to the limited training data. It is usually not difficult to perfectly fit an ECM to a set of pulsed current experimental data. However, it is often the case that the parameters are being overworked to make up for the model errors. This gives a model which is very good at recovering the training data, but may perform less well for a drive cycle in testing, as you can see in this bottom figure here. It would clearly be of great value to incorporate drive cycles appropriate to the eventual operation of the cell into the model training. We found that the parameterized models are often good enough for use with state of charge estimators, but more accurate and robust models are needed to improve state of power and state of health estimation. This approach also has impact on the experimental setup. For parameterization of thermal-electrical models, collection of data is usually done in a cooling rig to maintain a relatively constant temperature. These cooling rigs are often expensive and time-consuming to build. Additionally, a lot of information-rich data can be unused in the model training. For example, in degradation testing, the cell is often characterized at set points during a very long degradation test. However, there is a lot of information-rich data in between these set points that is going to waste. To overcome these issues, we've been investigating data-driven approaches for the ECM parameterization. In particular, we're incorporating a range of experimental data sets into the model parameterization, including drive cycles, characteristic to the end user. This improves model robustness and also acts to regularize the inverse problem. We also want to allow experimental data with many components of the operating point varying at once, so that the experimental setup is less constrained. However, since we are no longer working with pulsed or constant current load, the model parameterization does not reduce to a curve fitting problem, but the model parameters must be improved by iterated simulation of the ECM for the various experimental inputs, measuring performance of the model against the experimental output. An important aspect of our approach is how we break up the optimization problem into a set of smaller coupled optimization problems, which has the potential for parallelization. Without this, we would be left with a very numerically expensive global optimization. Given user-defined breakpoints in state of charge and temperature, for example, we portion up the data into sets of overlapping mini-experiments, which are local in operating point space. These are then used as the input for the optimization of the parameter values at each breakpoint. To mitigate model error, we reinitialize the hidden states in the ECM for each mini-experiment. These initial conditions must be solved for as part of the optimization procedure. Although this increases the dimension of the optimization problem, these additional degrees of freedom can be constrained effectively by communicating the model output from neighboring sets of data. This approach is much more computationally expensive and is not appropriate for online parameter estimation. However, we have found that the parameterized models obtain around double the accuracy in testing with drive cycles, if not more. You can see here the much more improved accuracy of the model in the drive cycle testing on the right-hand side of this figure. This improved accuracy and robustness translates into an improvement in the state estimation results. To conclude, we have developed a data-driven approach for ECM parameterization, which allows us to use a much wider range of experimental data for model training. The code we have developed is very adaptive, with details of the model and parameter dependencies being defined by the user. Currently, we are looking at implementing cross-validation procedures so that we can handle very large volumes of experimental data. This approach is being tested within the group for a range of experimental setups and will hopefully be released in the near future. Thank you for listening. I'm happy to take any questions.